So but today's topic is about randomized benchmark theories, and I will briefly overview the initial standard randomized benchmarking to the latest scalable methods. So I won't be going to be too much mathematical stuff. I will just like briefly overview all the methods. So this is the contents. So I will talk about motivation first, and then briefly discuss what the standard randomized benchmarking is and how those standard randomized benchmarking led to the initial variance or later variance, and so on and so forth. So the motivation is so these days a lot of corporates are trying to make the qubits larger and larger, and so in Google they recently published their 100 qubits processor, and also IBM made a 1,000 qubit processor last December. But we have to know if those processor is working right or not. So, but to benchmark the quantum processor, we need to think about the scalability about the benchmarking protocol, because as the number of qubits are really getting large, the scalability does really matter. So the first benchmarking protocol was called quantum process tomography. So it was suggested like around 1997. And it's just simple benchmarking protocol about just measuring all the density matrix of the qubits after some quantum processes. So we can measure or characterize all the uh, properties of the quantum process, but it is exponentially costly with respect to the number of qubits, and also it is sensitive to the state preparation and measurement errors. So it was a quite a good method for like 1 or 2 qubits, but if you have a qubit process about like 100 or thousands, it is just physically not approachable. So the alternative one is called randomized benchmarking. So it is just a method about measuring the average fidelity of some gate sets. And this method is a lot scalable than the quantum process tomography, and also it is robust to the state preparation and measurement errors. So this randomized benchmarking protocol is now kind of a golden standard in the industry right now. And the start of this theory was from the Clifford gates, which can make the unitary 2 design in the Hilbert space to measure the average fidelity of that Clifford gate set. And so the first theoretical paper was scalable noise estimation with random unitary operators in 2005. So their proposal was like, if we use the random unitaries with certain depths, we can measure the average fidelity as an exponential decay, and from that exponential decay, we can extract some fidelity parameters with respect to the number of gates. So this was the first theoretical work, and in 3 years later, first experimental work has been demonstrated using the trapped ion qubits. So the top figure in the right side is the first randomized benchmarking figures from the trapped ion qubit. So you can see that you can just measure the fidelity as the with respect to the number of computational gates. So and that fidelity decays as exponentially. So from that exponential decay, we can just simply measure the average fidelity. So that was the first experimental demonstration, and later on, yes. Yes. So, okay. So the question was how they measured the fidelity, because to measure the fidelity, we have to know the exact output. But so here, they only use the single qubit, and the exact output is just a excited state. So it is really easy to calculate the fidelity. So in 2011, after the 3 years after the first experimental demonstration, they um, theoretically advanced the first proposal as they showed the scalability, and also they proposed some exponential decay model that can handle the gate dependent and independent errors and time dependent errors using the perturbation theory. So so those are the first foundation and advances in the standard randomized benchmarking. So the protocol is really simple. So at first, you have to choose the Clifford gauge randomly about M or D depths of the Clifford gauge, and at the last layer, you just have to choose the Clifford gauge that can reverse the whole Clifford gauge as in front of the last layer, so that you can make the identity gate, or maybe you can just simply make the pi gate or so. So that's the step one, and step two is just implement those Clifford gates and measure the fidelity. So the last step is just fit the result of the average fidelity as a function of the exponential decay model. And from the exponential decay model, you can see that there's a0 and B0 and P. So here the P is PM's P part is only the fidelity part, and A0 and B0 are the just some constants, so that we can ignore the state preparation and measurement errors from those constant part, and we can just only measure the average fidelity of the gate sets from the P parameter. So this is quite simple, but at first we can only measure the average fidelity. So many people wanted to do something more from that standard version. So the first variant was called interleaved randomized benchmarking. So the motivation is simple. Just one wants to measure the individual gate errors other than just simple average errors. And how we can do that is just we can just simply interleave the gate of interest into the standard randomized benchmarking and just simply follow those protocol same, but with the interleaved gate sequences to measure the average fidelity. So therefore we can just simply do some mathematical um rel- use some mathematical relation. We can obtain the individual gate errors from those two decay parameters. So that's the first variant of the RB, and the second one is called simultaneous randomized benchmark. So motivation is also simple. Just one wants to measure the crosstalk between the qubits. And how we can do that is just simply implement that standard randomized benchmarking simultaneously and compare the results. So from it's just simple that if we have some crosstalk between qubits, then if we implement the RB simultaneously, then the exponential decay will decay much faster because of the crosstalk. But if we didn't have the crosstalk, then the exponential decay will be almost the same with or without the simultaneous sequences. So those, yes, question. Okay, so the question was what exactly the crosstalk? And the answer is there's no um, formal definition of crosstalk. It's just simple, but we can just say that it's a coupling between the qubits. I mean, we can say it's entanglement, but there are a lot, I mean, there are various forms about how does entanglement, because yeah, it's quite different. Yeah, it's really different. So, okay, so I'll move on. So those two were the first initial variants, and until 2024 from initial foundation, there have been a lot of variants about the randomized benchmarking. So at first, I told you that we only use the Clifford gate set, but there are other methods that can handle the non-Clifford gate sets also. And also in the first randomized benchmarking, we only address the gate independent or maybe gate dependent errors. And also we, we normally just think about the Markovian errors, but there are various types that can address non-Markovian or maybe gate dependent or maybe leakage errors or maybe some other things that. So those are in the left figure, those are the later variants about the randomized benchmarking, and today I will discuss some of them which are related to the scalability today. So in the Sandia National Laboratory, there is Quantum Performance Laboratory whose group is focused on making a benchmarking protocols, and they made some very good benchmarking protocols, which is very scalable and very noble these days. So I will just talk about what they made and how their developments are ongoing right now. So here's the thing. So first scalable method is called cross entropy benchmarking. And this is not developed from the QPL, but this is one of the top scalable methods related to the randomized benchmarking. And the second one is direct randomized benchmarking. So the second and third, fourth method is developed from the QPL group here. And they use some very similar theories. So it's kind of related, but the scalability is very different. So, okay, I'll just talk about it later. Okay, so the first method is cross-center benchmarking. So it is very simple way. We just implement the random gate layers and just calculate the true output distribution and calculate the linear cross entropy between that true output distribution with the measured bit strings and calculate the fidelity. So it is very simple, but if you use the non-Clifford gate, we cannot calculate the true output distribution very efficiently. So it is not so scalable if we use if we use the universal gates, but if we only use the Clifford gate, this cross entropy benchmarking is quite scalable. So this is good, but there should be better way to do this. So the first attempt from the QPR was using the stabilizer states. So unlike the standard randomized benchmarking, in the direct randomized benchmarking, the random layers, each random layer has a single depth, and these single depth random layers are very efficient than the n-qubit Clifford layer, which typically grows in size as the qubits get larger. So in the random layer part, this direct randomized benchmarking is a lot scalable than the standard randomized benchmarking, but still this method is not so scalable. We can only do up to like 6 or 7 qubits in practice. It's because those random layers are very efficient, but the stabilizer preparation and stabilizer measurement parts they grow exponentially. So as you can see in the right figure, like the polarization as the number of qubits grows, those depth zero part goes down quickly. So this is due to the stabilizer preparation and stabilizer measurement. So direct randomized benchmarking, it was the first very good attempt, but it still has a very bad part in uh, with respect to the scalability. So later on, they developed this mirror randomized benchmarking. So this method, it depends on the single depth, state preparation, and measurements. So the first problem in the direct randomized benchmarking has been directly solved. And also they use the circuit mirror technique that they don't need to calculate the true output distribution. They just have to mirror the random layers and calculate the final survival probability very efficiently. So this mirror randomized benchmarking was was been dem has been demonstrated to be very scalable, like across the universal gate or Clifford gate. But it has one flaw that it kind of underestimate the average fidelity as the number of qubits gets larger because the mirroring nature they possess some correlation between the random part and between the random and the inverse random part. So the correlation between those parts kind of lead to the underestimation of the error rates that it is scalable, but it kind of measure the error rates lower as the number of qubits gets larger. So the latest randomized benchmarking called binary randomized benchmarking is kind of advanced from those four from the mirror randomized benchmarking. So it has a local state preparation and measurement part with the single depth random layers. So by principle, it's very scalable, but very scalable, and also it is accurate. It measures the accurate average error rate compared to the mirror randomized benchmarking. So it is quite good, like scalable and accurate, but it can only handle the Clifford gate. So okay. Yes. The question was how much how long the depth should be in practice. And the answer is so yes, there is kind of a there might be kind of a lower bound in the lower bound in the depths of the random layers due to the because we need a entangling like high entanglement at the end, but uh in practice like 10 or I mean like below 100 random layers is enough, and normally if we 30 or 50 or 60 depths are sufficient to measure the exponential decay. So in practice it's quite that's not gonna be a bottleneck in the recent yeah. Okay. uh, okay, so I have to be go deeper about the random parts to answer the question. Okay, so the question was what kind of um, gate sets we use in the random layers, and the answer is it depends on the user. We can we can simply decide half x or half y or maybe g with just C NOT gate, or maybe you can just use C NOT and CG gate together. So there's no specific restriction about the choice of the gate set. You can just use the any kind of gate set, but we still need a entangling gate with the random single gate. And there will be sufficient to make the random layers. So it depends. Yeah. But there's no strict restriction about the choice of the gate set. Okay, so let's go back to the slide. So as I said, the binary randomized benchmarking is very scalable and accurate than the mirror randomized benchmarking, but it still cannot address the universal gauge. So we still gonna need a better randomized benchmarking protocol, but I don't know. Maybe the people in the QPR maybe develop a better way than this later, but this is the most um the latest developed protocol, so we might need like 1 or 2 years more to get a better protocol. Anyway, so let's compare those three protocols again. So as I said, the direct randomized benchmarking suffers from the stabilizer measurement and stabilizer preparation and measurement prior, so that the initial polarizations decays quicker than the mirror randomized benchmarking or binary randomized benchmarking. So between the direct or binary and mirror, the direct randomized benchmarking is not so scalable due to the initial polarization. And for the accuracy, the binary randomized benchmarking is a lot accurate than the mirror randomized benchmarking, as we can see in the figure E here. So those are just simple comparison with three methods. And the final method is called the cycle benchmarking. So it is um, kind of different from the randomized benchmarking, but it still depends on the randomization technique. So um, in the cycle benchmarking, there is a so in the like above like before those randomized benchmarking, we measure the average gate fidelities about the gate states. But in this cycle benchmarking, we measure the fidelity of the cycle, like fixed. We measure the fidelity of the fixed cycle, and to measure this fidelity, we use the local tolling method, which only uses the single qubit gate. So due to this local tolling part, this is very scalable. So as the number of qubits increases, we only need like single qubit gates, like, so it's just a O(n) complexity and very scalable, and we can deal with the universal gate as well. So it's very scalable, but it can only characterize certain like fixed cycle, that it is not a, we cannot say this is a holistic benchmarking. So it can deal with the universal gate and very scalable, but it is only restricted to the certain fixed layers. So it is not so perfect method yet. So those, how many it was, like 1, 2, 3, 4, 5 methods were the recent variants of the randomized benchmarking. And now I will talk a little about the randomized benchmarking protocol that can measure the average fidelity of the mid-circuit measurements as well. So far we only deal with the rotation gates or entangling gates, but these days, as we need a quantum error correction, or maybe we also do the um feed-forward operations a lot. So to do those kind of tasks, we need a mid-circuit measurement. And for the mid-circuit measurement, we also need a good benchmarking protocol to measure the error rates about the mid-circuit measurements. So there were so far like two methods about how to measure the mid-circuit measurements using the randomized benchmarking theory. And the first one is called a randomized benchmarking suit for mid-circuit measurements. So this is kind of a probing way that can characterize the error signature of the mid-circuit measurement as shown in the left down figure. Like, so there are error signature about the mid-circuit measurements. The first one is like no measurement induced error, or non-QND measurement error, or measurement induced control to qubit crosstalk. So we have various error signatures for the mid-circuit measurements as like this. And if we use the left top circuit diagrams, we can distinguish those various error signatures like right figures. So it's a probing way, but which use the randomized benchmarking protocols to measure the mid-circuit measurements error signature. So this was the first method, and the second method is Pauli noise learning for mid-circuit measurements that uses the cycle benchmarking, but just use the mid-circuit measurement in the fixed cycle to measure the Pauli noise of the mid-circuit measurements. So it is just, we can simply just say that using the cycle benchmarking, we can measure the Pauli noise of the mid-circuit measurements, and the underlying theory that enables how we can incorporate the mid-circuit measurement into the cycle benchmarking is quite complex. So if you want to know about that, you can just look into the reference. I will not address all those theory anyway. So those two were the randomized benchmarking based benchmarking protocol for the mid-circuit measurements, and the presentation is just over. So if you have any questions in those slides, you can ask now.